Good afternoon, students. Let us start the lab class. Today's experiment is RC phase shift oscillator. Let me tell you briefly about oscillator, because in the theory class it might not have been covered as of now. So, let us say we have an amplifier. When we have an amplifier, let us say a portion of an amplifier's output is taken back by means of a passive network, and let us say it is connected to this passive network and it is given back to the input. So amplifier is going to give a gain of A, and let us say a small portion of that output, some percentage, let us say I'll write the percent symbol itself, some percentage of the output is given back to input along with the phase shift. Imagine input will be in this form and all common emitter amplifiers are will give a phase shift. So you can see the output is 180 degree out of phase. Now we will take the portion of this output back to input, but with the phase shift. That means with a small percentage. Now you can see that this particular output waveform and the feedback waveform are out of phase because the feedback network is going to produce this phase shift of 180 degree. Now you can see this particular signal, feedback signal, is in phase with the input signal. So naturally what happens is this input signal and the feedback signal are in phase. The input signal is going to increase its amplitude. When the amplitude of input signal increases, that is going to be amplified, and the amplified output is going to come back again. So this way it goes on. After some time, even if you remove this input signal, let us say you remove this input signal, output will still be there because this would have been amplified again and again and again. Now such circuit which can produce oscillations on its own is called an oscillator. I gave you a brief idea. More about oscillators will be discussed again in theory classes. So now, amplifier with positive feedback is an oscillator. That is the concept here. Amplifier with the positive feedback. In the sense, amplifier's output has to be taken by means of a network, and this network should take a small percentage of the output. Along with that, this feedback network has to produce a phase shift of 180 degree also, because the amplifier itself is producing a 180 degree phase shift. We are always using common emitter amplifier only. So in that case, amplifier with a positive feedback is an oscillator. Now what is the use of an oscillator? Can anybody tell me? Because it is a general knowledge topic here now. Amplifier's use is anyhow that a small signal is going to be resulting in a larger signal. That is the purpose of the amplifier. What is the use of the oscillator? Can anybody tell me? You can unmute and tell me. Or you can put it in the chat box also. There are 14 students and nobody is telling. Okay. When nobody is telling, I have to tell. You will be listening to FM radio daily, right? You will be listening to all types of music, which is broadcast by the FM radio. Now in FM radio, you have many channels. Each channel has a particular name, but the channel also has a basic frequency which they mention. 92.8, 93.4 megahertz, that way they mention. That 92.8 megahertz is the radio carrier signal. On top of the radio carrier signal, the modulating signal is there. You have studied already about modulation in the first year. As a general block diagram, you have already studied in basic electronics. So, modulator is the one which is going to have a radio carrier and it will have a low frequency modulating signal. If I have to give a real life example, we daily come through vehicles, or we travel through vehicles. Vehicles are high speed and we are low speed. So what we do is we sit inside these high speed vehicles and we move all the way. Whether we go in two-wheeler or four-wheeler or BMTC bus or metro train or even a flight, all those are our carriers. In the same way, if a low frequency signal has to be transported to the destination, it is going to be used inside a high frequency carrier wave. Now that high frequency carrier wave is required to transmit the low frequency audio wave. Now, for example, when you are using your mobile phone, the mobile phone is going to use a 2.4 gigahertz carrier signal. Inside this carrier signal or through this carrier signal only, your voice or your SMS or your WhatsApp message or your any type of video sharing or photograph sharing, whatever, whether it is data or video or text or voice or sound or music, in whichever way, all that is going to be transmitted by using this radio carrier of 2.4 gigahertz or 2400 megahertz. Now, your mobile phone is a digital communication device, whereas FM radio is a analog communication device. But in both of these devices, or both of the equipments, communication equipments, so to say, in all of the communication equipments, a carrier wave is required. Amplifier is the one which is increasing the amplitude of the input signal, but that amplified output is at the destination. In between, the signal has to go from one place to another place or from source to destination. We require a carrier wave. Who will generate the carrier wave? Now, the circuit which generates this carrier wave is called as an oscillator. That's all. So, oscillator is the circuit which generates this carrier wave, high frequency carrier wave. We use this again to transmit the modulating signals. The modulating signals may be voice, video, data, text, music, in whatever way. So that is the use of an oscillator. Oscillator is an integral part of every electronic communication equipment, just like an amplifier also is an integral part. And oscillator is constructed using amplifier itself. Amplifier with the positive feedback is going to be an oscillator. Now, the symbol for oscillator is simply like this, one circle with one symbol. Sorry, let me write it better. One circle along with the symbol like this. This is the symbol of oscillator, and oscillator will have only output. It will have no input. But right now I told amplifier with the feedback, positive feedback is an oscillator, and the feedback circuit will have phase shift also. So the feedback signal along with the input signal, when they are in phase, gradually it will get amplified. After some time, even if you remove the input also, the feedback signal itself will work like input. That's what I told. But now I am telling that oscillator will not have an input signal at all. It will only have an output signal. For example, in your mobile phone, if you have the oscillator, its output is 2.4 gigahertz. That is the output. Now my question to you once again is that without the input, how can output come in case of an oscillator? Can anybody tell me? Without the input, how can output come out of an oscillator?
Generating the thing.
Yeah? Rohit, tell more clearly. No, we are unable to hear you.
The oscillator itself starts generating.
Yeah, which one transistor generates?
Oscillator itself.
Yeah, oscillator is amplifier with the feedback, right? So it is generating, correct. But without the input signal, how it is generating is the question. Fine. Sachin has given the answer due to the noise distortion at the input. Fine. Actually, the oscillator will not have any input at all, but there is a noise there. We are using a device, active device inside an amplifier. Now, as soon as you switch on, the circuit will take its own time to stabilize. The amplifier along with the feedback network, that is now a closed loop circuit. That closed loop system takes its own time to stabilize. In the sense, as soon as you switch the power on, transistor will not come exactly to the middle of the active region. It will take some time. Until then, there will be some minute switching noises inside the device itself. Now, these noises also get amplified in the beginning. Now, in case of oscillator, when the noise is amplified, when it is coming back to the input, now there is that feedback network. That feedback network is a frequency selective network. Means the feedback network is going to work at a particular frequency only. I'm going to discuss that later on. So when that feedback network, remember the feedback network is a frequency selective network. It is a phase shifting network, and it is also taking a portion of the output back to the input. But the feedback network is a passive network. There is no active device there. It's a network made up of resistors and capacitors only. But it is going to introduce a 180-degree phase shift, and then it is going to take a small portion of the output back to input. At the same time, it is going to be a frequency selective network. Now, when it is frequency selective, even though the device contains all types of noises from 0 till infinity, all types of noises, because noises do not have any particular frequency. Noise will be ranging from 0 till infinity. Within that range, when the noise is there within the device, a minute noise, maybe few nanovolts or few picovolts or few femtovolts of noise. Now that noise gets amplified by the amplifier, and through the frequency selective feedback network, when it goes back, we decide the frequency of the feedback network now. Based on that, only that particular noise will be fed back. When that noise is fed back, that noise again gets amplified. Now that noise is a wanted noise for us. For example, in this case, this 2.4 gigahertz is wanted by us. But the noise which is inside the device is from 0 till infinity. In between, there is this 2.4 gigahertz. We choose a feedback network which will work only in 2.4 gigahertz. That way, only 2.4 gigahertz goes back as again input to the amplifier through the feedback network. And that gets amplified, and after a few seconds, we will have the stabilized 2.4 gigahertz output. So this is the answer. The answer is that oscillator will not have any input at all. The switching transients which are within the active device themselves are going to be amplified. But as the feedback network is a frequency selective network, only at a given frequency, we decide what frequency we want. And based on that, it will get amplified by the amplifier. And then we have a oscillator. So with this brief theory about oscillators, let me continue further with our circuit diagram. Now this is the circuit diagram of our today's experiment, that is RC phase shift oscillator. You can see here, this whole circuit is RC coupled amplifier. You are already familiar with this. It has been discussed so many times in the theory class. It has been discussed even in the lab classes. You know this. This is a voltage divider biasing network, and we have a bypass capacitor. This whole circuit is nothing but an amplifier circuit. Now to the amplifier we have connected, you can see one RC, one CR, one more CR, one more CR. Let me tell you. No, let me erase this. Let me write this network now. There is this C. You can see from the output it is coming to a capacitance. Then from this C, there is one R connected to ground. Then there is one more C. One more C. Then there is one more R that is connected to ground. And there is one more C. Ideally, there must be one more R connected to ground. Ideally, it must be like this. So now, you can see from V0 back to the base of the transistor, typically there must be a 3-stage RC network. Now, each RC network is going to introduce a 60-degree phase shift. So, there are 3 networks here. Each one is going to introduce 60, 60, 60. So, it is going to become totally 180 degree. As I told you, the feedback network has to introduce 180 degree phase shift. Amplifier is introducing 180 degree phase shift. Feedback network has to introduce additional 180 degree phase shift, so that the output which is coming back and the previous signal and the present signal, that means the feedback signal and the initial signal, will be in phase. That is how the same signal will get amplified again. It will come back again, it will be amplified, it will come back. After some time, the system will stabilize so as to produce a output like this. AC waveform or sinusoidal waveform like this. So this is going to be the output. So theoretically, the phase shift network, not the phase shift network, the feedback network should introduce 180 degree phase shift. That is why we connect 3 CR networks. Why we connect CR? Why don't you connect RC? We cannot connect RC here. If you connect capacitor connected to ground, all the signal will go to ground only. We want the signal to be going back to the input. That is why we cannot connect R and then C. We are connecting C and then R. I hope this point is clear. We are connecting resistance to ground, capacitance in series. If we do the reverse, actually RC network is going to introduce 60 degree phase shift, whether it is CR or RC. It is going to introduce a phase shift. But if we connect it as RC, then capacitance is connected to ground, all the signal will go to ground. That is why we are connecting capacitance in series, resistance in parallel. Now we connect these 3 networks, it is going to introduce 180 degree phase shift. So the first purpose is fulfilled, that the feedback network should introduce 180 degree phase shift. That is the first purpose. The second purpose is portion of the output waveform should go to the input. That is also fulfilled. How? We are choosing a capacitance of a very lower value. So this capacitance will have its own XC. It will have its own reactance. In a given frequency, it will have X equals 1 over 2 pi FC. So we choose the value of C in such a way that this capacitance will have some reactance. Now because of the reactance, there are 3 capacitances which are going to introduce this reactance. So all the output will not come to the input back. Only a percentage or a portion of the output is coming back. That is the second purpose of the feedback network. That is also fulfilled. So the first purpose is 180 degree phase shift. Second purpose is percentage of the output back to input. Now the third purpose is the feedback network has to be frequency selective. Now this RC is basically frequency selective. We have already seen in the 3rd chapter of AEC, right? I only have taught you the 3rd module of AEC, where we have a formula for F equals 1 by 2 pi RC. We have seen that RC circuit itself is frequency selective. That is how all the 3 purposes of this particular feedback network are fulfilled. And as soon as you connect this particular circuit, as soon as you switch it on, if all the connections are all right, now it will produce an output directly on its own. There is no input signal here. Now my question is, look at the network which I have written, look at the network which is there in the circuit diagram, and can someone tell me, instead of this last R, there is supposed to be this last R. Instead of this last R, why do we have this potentiometer? There was supposed to be one resistor connected to ground. Instead, we have a potentiometer connected in series. Can anybody tell me why? In the textbook, you will find only the circuit which I have written at the right side, because this is an ideal circuit. But in the lab, this ideal circuit will not work at all. In the textbook, he says that each RC network is going to introduce 60-degree phase shift. So 3 RC networks are going to introduce 180-degree phase shift. But in the lab, it will not work that way. In the lab, we have to connect the circuit like this. Can you tell me why?
Sir, is it because we can vary the resistor in order for the frequency we want?
To some extent, that is all right. But let us say we don't want to vary the frequency. We want to have a constant 5 kilohertz. Imagine the output of this circuit is around 5 kilohertz. Now we want a constant 5 kilohertz. We don't want to vary because all carrier frequencies are going to be constant, right? Now in your mobile phone, 2.4 gigahertz, that carrier frequency is constant throughout. It is a worldwide standard that all the 3G phones will use 2.4 gigahertz. Even in FM radio, 92.8 megahertz, if it is the carrier wave for a particular channel, that is going to be fixed lifelong for that particular channel. So we will not be varying the frequency at all. That is not the purpose here. Of course, when you vary this slightly, the frequency will vary. That is true, because the value of R will change. But that is not the exact answer. Anybody else? This answer is slightly complicated. I'll tell you the answer anyhow later on, but I want the students to think. Okay, let me tell you the answer. The answer is slightly complicated. Let me clear the screen. Now let me write once again. See, this is the amplifier now. Now you have this feedback network here. This complete feedback network, CR, CR, CR is the feedback network. And output is coming back to the feedback network. It is going back to the input. Now, when we discuss an ideal amplifier will have a very high input impedance, very low output impedance, and the feedback network will introduce a 180-degree phase shift where it is CR, CR, CR. That is fine, but we are not dealing with ideal amplifier. Our lab or this BJT amplifier which we use is a practical amplifier. In the practical amplifier, you will have a ZI inside, right? You will have an input impedance, ZI or RI. You will have an input impedance inside the amplifier, then you will have an output impedance also. And input impedance is in terms of few kilo ohms. We had some exercises in the very first module of theory class where we had seen the input impedance of the order of 2 kilo ohms, 2.5 kilo ohms, 3 kilo ohms, that way. You remember it is R1 parallel with R2. See, R1 parallel with R2 parallel with beta into small re. Now that is going to be some few kilo ohms. Let us say the input impedance of this amplifier is around 2 kilo ohms. Imagine it is around 2 kilo ohms here. Now we have connected a 4.7K here. We have connected a 4.7K here. If at all we connect one more 4.7K here in parallel, that 4.7K will be in parallel with this 2K. You understood? Let us say we connect a resistor, the third resistor in parallel, that 4.7K will come in parallel with the input impedance of the amplifier itself, that is 2K. So 4.7K in parallel with 2K. Now our formula will deviate, right? Our formula is F equals 1 over 2 pi RC, where R is supposed to be a constant value. Now the third resistor will have problem. How do we solve it? We cannot solve it so easily, because the input impedance of an amplifier is not a fixed quantity. When let us say 10 batches in the lab work with the same circuit, with the same transistor BC107, with the same values also, all the 10 batches will not get the same input impedance of 2K. Why? Transistor to transistor, beta is different, and resistors will have tolerances. Each resistor here has got 5% tolerance, and transistor to transistor, beta is different. Even though we are going for a voltage divider bias, where we can say that beta can be ignored, still for the impedance calculation we have R1 parallel with R2 parallel with beta into small re. Now R1 and R2 will have their own tolerances of plus or minus 5%. And the transistor will have a beta which will be different from transistor to transistor. So in such a case, if 10 batches are conducting the experiment with the same transistor, you will have 10 different values of input impedance. Input impedance is a dynamic quantity that cannot be having a fixed value. Now in such a case, when we don't know the actual value of the input impedance, how do we fix the external resistance here? So the solution which we find in the lab is, we connect a potentiometer in series. Now let us say the input impedance here is 2K. Let us say the input impedance here is 2K. Now, when you switch on this circuit, immediately you may not get the output at all here, because this may be 10K. 10K, here it is 2K. 10K, it is in series with 2K. You visualize Zi with respect to ground here. So 10K is connected to 2K. It will be totally 12K. Whereas here it is 4.7K, 4.7K. So their phase shift problem is there. Even the fraction problem is there. Even the formula problem is there. All the C are having equal value. When all the C are having equal value, all the R also are supposed to be equal value. Now, output will come only when you tune this potentiometer to 2.7K. See, when you tune this potentiometer to 2.7K, 2.7K in series with 2K is 4.7K. This 2K is internal to the amplifier. This is in series now, potentiometer is in series. So when you fine tune this potentiometer, when this reaches 2.7K, internally if it is 2K, 2.7K plus 2K is 4.7K, that is when the exact phase shift happens and oscillator starts oscillating, output will be available. Now I gave an example of 2K, but actually we don't know what is the value of input impedance, right? Otherwise you may say, if this is 2K, we can connect a physical resistance having 2.7K only. Yeah, that is possible only if we know the input impedance of the amplifier. But it is going to be different for each circuit. That is why our solution is, we connect a potentiometer in series and we fine tune it in the lab. Then when it matches with the value of 4.7K, then the circuit starts oscillating. That is why in the lab we have this potentiometer. Otherwise, you have already understood the basics now. Let me go to the design part now. This is the observed waveform. We will choose capacitance as 2.2 nanofarad, resistance are 4.7 kilo ohms. This formula is slightly complicated. I will not discuss the formula here in the lab class now. Anyhow, in the theory class, in module 4, we are going to discuss about why the formula for phase shift oscillator is like this. So, there is a formula for this output, that is 1 over 2 pi RC square root of 6 plus 4K, where K is RC by R. This is again a typo mistake here. K is RC by R. That means you have a resistance at the collector 2.2K and you have a resistance at the bottom 4.7K. That ratio is called K. I am not going to go into the details of this ratio in this lab class because it is meant for the theory class only. So that way we have this value K, and when we substitute this value K here, 6 plus 4 into K into that square root of that into 2 pi RC, 1 over that is going to be the output frequency. Now, there is a condition that HFE or the beta of the transistor has to be greater than 4K plus 23 plus 29 by R. This is a crazy equation. We don't have a proof for this equation in our syllabus because the proof is quite big. Just like in network analysis, you have to go for a Laplace transform or frequency domain approach of the circuits. Even for this circuit, we will have to go for a frequency domain approach so as to derive this equation. Even in the theory class also, derivation of this equation is not there because it is much more complicated. Those who are interested can always ask Googleshwar. Googleshwar will tell you everything. By the way, I think I asked some question. I don't know. I don't remember whether I asked this lab class or some other lab class. I had asked that you should find out from Googleshwar. I don't know. Let it be. So, this beta is greater than, beta has to be greater than 4K plus 23 plus 29 by R. That is why we have chosen a transistor called BC107 here. This BC107 will have a beta which is more than 120. That way, it is satisfying these conditions. So that way, we have the formula for this circuit, that is F naught is 1 over 2 pi RC into square root of 6 plus 4K, where K is RC by R. Now let us choose the transistor BC107 whose minimum HF is 120. As I told you, it is mentioned here. Now HIE is in the range of 2 to 3 kilo ohms. Let us choose R equals to 4.7 kilo ohms. So that K is 2.2K by 4.7K. It has to be 4.7K. It's around 0.47. So HF is 4 into 0.47 plus 23 by 29 divided by 0.47. HF is greater than 87, which is satisfied because HF is 120. So the condition is satisfied. Let our designed frequency be 5 kilohertz. So 5K is 1 over 2 pi into R into C. 1 over 2 pi RC is square root of 6 plus 4K. Now we have to choose C. See, C is multiplied here. We want 5 kilohertz, right? So it has to be C equals 1 over, again, don't worry about the upper expression. My colleagues who have done this lab manual, they have not verified. I don't know who has done it, but they have not verified correctly. But look at this C value. C equals 1 over 2 pi into R into F. F is 5 kilohertz. Again, this C should not have been there. They have put C everywhere here. Here C should be there, 5K should not be there. They have done a copy pasting again. Anyway, 6 plus 4K. So we get C around 2.41 nanofarad. The nearest capacitance is 2.2 nanofarad. So the capacitance is now, we choose the standard value as 2.2 nanofarad. When you choose the standard value 2.2 nanofarad, we will not get exactly 5 kilohertz because we are changing the capacitance. But it doesn't matter because we are conducting the experiment for the sake of understanding the oscillator circuit. It is not going to be used in any other appliances or electronic applications. It is only for the sake of lab. So we choose the nearest standard value. But if it is required for the actual application, we cannot have a standard value. We should have an accurate value of 2.41 nanofarad only. Okay. In the lab, we use the standard value of 2.2 nanofarad. In this way, what you have to do is, the experiment is really very simple. In the sense, first you connect this RC coupled amplifier, you are already familiar with that. Then, without actually connecting this potentiometer, you can connect all these other things also. Without connecting the potentiometer, switch on the circuit. When you switch on the circuit, what should be the DC voltage here? Can anybody tell me? Without connecting the potentiometer, you should check the DC voltage at the collector of the transistor. What should be the DC voltage at the collector of the transistor? There are 18 students now. Anyone should answer now. Oh, come on. In theory class, I had told it hundreds of times. Even in the lab class, I have told. All the 18 students must be sleeping. Nirmit is there, Harshit is there, Rohit is there. Sachin answer. You will have to answer.
So 1 by 2 pi fc.
1 by 2 pi fc, that is a frequency. I am asking what must be the voltage at the collector without connecting the potentiometer. You should not connect the potentiometer. When you do not connect the potentiometer, there is no feedback, isn't it? There is no feedback. This is only an amplifier. Now, if it is an amplifier, when you switch it on, what must be the DC voltage? Obviously, it has to be around VCC by 2. Because the transistor is going to be in the active region, right? So, obviously, the collector must be around 5 volts. But including this voltage across the RE, it must be around 6 volts. 5 to 6 volts. In between that, it should be there. Because any amplifier is working only when the transistor is in the active region. It is half on. So that is how you have to verify the connections. Before connecting the potentiometer, you can connect all other things. Without connecting the potentiometer, switch on the circuit and check the voltage at the collector must be between 5 to 6 volts. Then it means that the transistor is in the active region. Now it is an amplifier, right? Later on, switch it off and again connect this potentiometer here. It is only a single connection there. Connect the potentiometer's other end to the base, then switch it on. After switching it on, fine tune this potentiometer so that the value will reach to 2.7K plus 2K here. Then automatically at the output, oscillations will start coming. That way, this experiment is really very easy to conduct in the lab. There is not much of a work except for the connections because there is no input, there is no gain measurement, there is no frequency response here because this is an oscillator now. Simply the output will come and you will have to measure the frequency of the output. It has to be nearer to your theoretical value. We had designed it for around 5 kilohertz. You will have a slight variation. You will not get 5 kilohertz exactly because we are using a standard value of 2.2 nanofarad. Instead of 2.41 nanofarad, we are going to use 2.2 nanofarad. So you will have a slight change in the frequency value. You can measure it. You can see this frequency in the oscilloscope. In the oscilloscope, you can measure the period of the waveform. 1 over T is going to be F. That's all. That is the first part of the experiment. Next, or the last part here now, we are going to measure the phase shift here. Now, theoretically, we have seen that this network is going to introduce 60 degree. This network is going to introduce 60 degree. Then finally, this potentiometer along with the input impedance of the transistor or amplifier is going to introduce 60 degree. Theoretically, we know. Practically, we want to measure. Practically, we have this 4.7K. Here we have 4.7K. Here we have 2.2 nanofarad. But all of them have tolerances, right? The resistor will have plus or minus 5% tolerance. The capacitor also will have plus or minus 5%, sometimes plus or minus 10% tolerance. 2.2 nanofarad may not be exactly 2.2 nanofarad. 4.7 kilo ohms may not be exactly 4.7 kilo ohms. But net effect will be same. Net effect of the circuit will be totally 180 degree. Otherwise, the oscillator will not work at all. So that way we have this potentiometer. This potentiometer is going to help us in totally obtaining 180 degree phase shift. But the value of this R may not be exactly 4.7K. Value of C may not be exactly 2.2 nanofarad. So for that purpose, we want to measure the phase shift between this 0.1 and 0.2. Later on between 0.1 and 0.3. we need not measure between 0.1 and 0.4 at all. We need not. Why? Between 0.1 and 0.4, only when it is 180 degree, then only it will start oscillating. So obviously it is going to work. We will have to measure the phase shift between 0.1 and 2, then between 0.1 and 3. Between 1 and 2, ideally 60 degree. Between 1 and 3, ideally 120 degree. But practically, it may be slightly different because of the tolerances of the devices. However, between 1 and 4, it has to be 180 degree because using the potentiometer, we are going to fine tune the value. Now, how do we measure the phase shift is the question. For that, what we do is, we put the oscilloscope into a mode called XY mode. In the physics lab, you have already worked with oscilloscope. So you know how to use the oscilloscope. Oscilloscope has got a X deflection plate, it has got a Y deflection plate, means horizontal deflection plate, vertical deflection plate. In fact, in the oscilloscope, it is the beam, electron beam, which is hitting a phosphorescent screen at the front. When the electron is hitting the phosphorescent screen, on the screen, you will see the dot there. That visible light is emitted from the phosphorescent screen, or so to say fluorescent screen. That is because of the hitting of the electron beam to the screen. Now that beam can be made to move up or move down, or made to move left to right by means of vertical deflection as well as horizontal deflection. Normally, we will not touch the horizontal deflection. Normally, when you switch on the oscilloscope, you will see a horizontal line. Actually, it is not a line. It is a point which is moving faster. Electron beam, where it is hitting the screen, you are seeing a point. Now, when you increase the times per division, the point will keep on moving in a faster way, and it is moving left to right, left to right, left to right. Because of the persistence of vision of our own eyes. Anybody knows what is the persistence of vision of our eyes? What is the value? Anybody knows? The value of persistence of vision of our eyes is around 16 milliseconds. Means, if anything is moving faster than 16 milliseconds, we will not be able to detect the movement. We will see it as a continuous movement. Because of the persistence of vision only, we are able to enjoy the movies. Actually, the movies are not movies. They are continuous movement of still pictures. But we are seeing the movie as such because it is moving much faster. Same way, in the oscilloscope, when the beam is moving, which is much faster than our persistence of vision, then we see a horizontal line. For that, we have a waveform called sweep waveform inside the oscilloscope. Now, in this experiment, what we do is, we put the oscilloscope into something called XY mode, phase shift measurement. Okay, here, rig up the circuit as shown, then, observe the Lissage's pattern. It is called Lissage's pattern. Lissage's pattern in the sense, we will not put the oscilloscope in the normal default mode. Even the horizontal deflection also, we only take control. Vertical deflection, anyhow, we connect the input to the front probe. Through the probe, we connect it to the front slot there, front connector there. But for measuring the phase shift, what we do is, we put the CRO into XY mode, where we connect one point to node 1 to Y channel, node 2 to X channel. You can see this node 1. This node 1 is connected to Y channel, node 2 is connected to X channel. When we physically conduct the experiment, that time we will tell you how to actually do it. Now, for the sake of this online lab class, I am discussing these things in detail. Otherwise, when we start the offline lab classes, at that time you can physically do all these things. Now, we connect that Y channel probe here, then X channel probe here, and we put the oscilloscope into XY mode. When we put the oscilloscope into XY mode, we will see a figure there. That is called Lissage's pattern. Let me write the pattern here. We will see a pattern like this. which will be shown in the front screen of the oscilloscope. This pattern is called Lissaj's pattern. Now, in this Lissaj pattern, you will have to move it to the center of the oscilloscope. When you move it to the center of the oscilloscope, you will have to measure this. You will have to measure this particular vertical height. Then gradually you have to move this pattern completely to the left side. Actually, I have not written it accurately. Let me write it slightly accurately. The Lissaj's pattern looks like this. Okay. Now, let us say we connect through mouse. I am somehow writing the line. Let us say we measure this particular point. Later on, again we move. Actually, this pattern has to be slightly like this. It has to be like this. It is gone. Anyway, it is gone. Okay. Now it is clear. Let us say, no, this has to be moved down. Now this is the origin and I have this dimension here. Measure this particular height. Let it be y1. Then move this slightly this side and measure this. Let it be y2. Now this is that Lissaj's pattern because of the xy mode, because of the two signals, one signal at node 1, one signal at node 2. Now in between these two signals there is phase shift. Recall the circuit diagram. Between node 1 and node 2 we are measuring the phase shift because it is a CR network now. We are putting both the signals into the oscilloscope, one to the horizontal deflection, one to the vertical deflection. That is when we see this Lissaj's pattern. When we see this Lissaj's pattern, you have to measure y1, you have to measure y2. Now, the phase shift theta is given like this. Let me stop annotating. Let me show you the formula. Theta is given as sine inverse of x1 by x2. It can also be y1 by y2. You can measure the x direction dimensions also, or you can measure the y direction dimensions also. They will be one and the same. Why? Because that Lissaj's pattern will be symmetrical with respect to x and y axis. So you can either measure x1, x2, or you can measure y1, y2. See, both are given here. Theta equals sine inverse of y1 by y2, or theta is sine inverse of x1 by x2. That you are measuring here between 0.1 and 0.2. Okay. Between this 0.1 and 0.2, you are measuring that y1 and y2. Sine inverse of y1 by y2 will be the theta. Approximately you should get 60 degree, but practically you may not get 60 degree. You may get 58 degree or 62 degree, depending upon the values of these components. As I mentioned already, they have the tolerance. Next, keep this pin 1 there only, 0.1 there only, and move the other probe to 0.3. Now, this will remain in that Y deflection plate only or Y channel only. You will be moving this to the X channel to the point number 3 now. You will see another Lissaj's pattern on the screen, but you will be seeing it in the second quadrant now. I will show you. Now, when you connect the oscilloscope between 1 and 3, you will see a pattern which is like this now. It is in the other direction now. It will not be in this direction. Earlier it was between quadrant 1 and quadrant 3. Now this pattern will be between quadrant 2 and quadrant 4. The reason is, earlier it was 60 degree phase shift. Now it is 120 degree phase shift. Naturally from first quadrant it moved to second quadrant because of the phase shift between the signals. Now here also procedure is same. Measure y1 and measure y2. Okay, measure y1, upper one is, lower one is y1, upper one is y2. Measure y1 and y2. And the procedure is same. Only thing is, Now, when you find this answer, you will have to make it as 180 minus, because now the Lysage's pattern is in the second quadrant. So 180 minus whatever value you get, that will be the phase shift between 1 to 3. You will get approximately around 120 degree. So this is how you are going to measure the phase shift between these different segments of the feedback network. There ends our experiment for today. That's all. Once you get the Lysage's pattern, between nodes 1 and 4, anyhow, it is going to be 180 degree only. You will not be able to observe it as such. But if it doesn't become 180 degree, oscillator will never work. So theta 2 is to be observed to be 120 degrees. Somewhere nearer to 120 degree, you will get the value. Finally, you are going to tabulate the results as frequency of oscillation f0 is what value you got, then theta 1 what you got, theta 2 what you got, theta 3 has to be obviously 180 degree only, otherwise the oscillator will not work. With this, I am coming to the end of today's experiment. If any of you have any questions, you can ask me, or else we will conclude today's class. Okay, I think students have no question at all. Let us conclude the class. Prithviraj sir, attendance is taken?
Yes, sir, it is taken, sir. Attendance is taken, sir.
Okay, then we will conclude today's class. See you in the next class. Until then, take care and goodbye.